Alright, let's continue with part 2 of this short surface topography lecture. In this part we will discuss a little bit how to quantify the roughness. We can start by looking at this picture. If you use a 2D type of measurement, a stylus instrument, you may get a profile, a measurement like this. You can see the roughness here, but on top of that you also have the shape, the form of the actual component. In this case it's a gear tooth, and you can see the scale here. It's almost 2 millimeters, and if you try to use this what is called primary profile to measure the surface roughness height, the surface roughness height will be something between -4 to 2 micrometers, so it's more than 6 micrometers, and that is not at all representative for the actual roughness. So of that reason you must filter the waviness away, and I made here just my own filter to took away some kind of form here, and that's the waviness, and then what is left is the roughness. So this is what we actually use to quantify the roughness itself. This is normally built into these stylus instruments. If you now have the roughness profile available, then you can start quantifying it in different ways, and the very most common is the RA, the average roughness, which is actually you take the absolute value of the roughness profile, and then you compute the average height of that profile. So you take all the negative. You first of all you find the center line average here. That's the line where you have as much solid above the line as you have valleys below the line. That's the center line average. If you then put all the valleys, make them change the sign of them, then you get only positive profile, and then you take the average height of that. That's a kind of measurement of the height of the surface roughness. It's very much used. I will come back to that later. It's not very useful maybe for tribology, but it's a measurement. Another way to do it, another way to find an average value, is to, instead of taking the absolute value, you take the square. You use the power 2 of the profile, then everything is positive again. You compute the average of that, so it's a root, and then you take the root value of that. That's the root mean square. And there is a difference between these values, but they measure approximately the same thing. From a tribological point of view, it's maybe you remember from contact mechanics that the slope is actually more important. How sharp the asperities are, that's more important. So there is also a measurement of the slope, and in this case this is a root mean square slope, and this is an interesting parameter because that one we have seen has a closer correlation to tribological phenomena like friction and wear. That's something to remember. Slope is more interesting than height. Coming back to this RA problem, is that this is a classic picture of 6 different surface roughness profiles. They have all the same RA value, but you can think about it. If you which one do you believe is the best one from a tribological point of view, and which one is the worst one? Well, I think it's pretty easy to understand that intuitively, or you can also think about making a surface like this, and then you take your shoes off and you walk on these surfaces, and you may find that, for example, profile C is not that nice to walk on, but while maybe profile D is much better. but still the RA value is the same, so the RA value is not very good to describe the surface roughness from a tribological point of view. And of course, if you have a landscape like this, this is a ground surface, this is a special treatment called chemically deburred. You have many ways to describe a landscape like this. It's as we have discussing the roughness height, the slope. You can also talk about some kind of wavelength here. You can start counting the number of peaks. You maybe if you focus on one of these peaks, what is the summit radius? Because from contact mechanics, you remember that a small radius will penetrate the surface much more than a big radius. And also the valleys play a role. If you lubricate this system, your lubricant may be stored down here in the valleys, and that has some effect too. And some people talk about valley connectedness. So if the valleys are connected, then the lubricant may escape to another valley. But if they aren't, the lubricant can't escape, and then it lubricates instead. And the lay, the direction of the grinding marks is also could be important. So in this case, the RA again is the same for these two surfaces, but still they look very different. So one better way to describe the surface roughness is to use the amplitude density function and the bearing ratio curve, which is also called the Abbott-Firestone curve. So, and the definition of that is the kind of probability to find a point on the surface at a certain height. So if you have a height profile like this, you establish your centerline average like this, and then you just count the probability to find the profile at a certain height. For example, up here it's 0 probability, while here it's very low, but there is some probability starting. But around the centerline average, the probability is the highest. If you then use this probability curve and you use the cumulative distribution instead, you get the bearing ratio curve. So that tells you if you move a plane through the profile like this, here you start touching the surface, and here you have passed 50% of the profile, and here you have passed 100% of the profile. So this is actually the integral of the probability curve that gives you the bearing ratio curve. That also tells you about where are the peaks, where are the valleys, how many valleys do you have, how much peakiness do you have. So the bearing ratio curve is used to define a number of other parameters, like the core roughness depth, which is it's a little bit tricky to find this line. You fit, this is the bearing ratio curve again, and you try to fit the secant, which is 40% of the total length of this secant is 40%, and you move it from starting here with this end starting here, and you try to, and you take the secant and the 40%, then it will cross here, and then you try to find the secant with the lowest, smallest gradient, because around here it has the smallest gradient. Here it starts to increase again, and then you fit a line to that secant, and that defines some parameters like the core roughness depth, and also the peak or the reduced peak height, and the reduced valley depth here. So the RVK and RPK and RK are used in industry pretty often to define the surface roughness, and this is definitely more of interest for a tribological surface. So if you have a low RPK, for example, then you don't have that many peaks, and it's like walking on a surface without peaks. That's pretty nice. While you have a big RVK, could be good because you want to store lubricant down in the valleys. So bearing ratio curve I can recommend. This is again from Indexator. Just using this, you can compute these curves also for by using the 3D tool. And here you can see that the core depth, core roughness is lower for this milled surface than for this turned surface. There are some attempts also to use skewness and kurtosis of the profile. So and the skewness is defined like this. Instead of having a factor 2 here, when you or factor 1 in some cases, you take the factor 3 and the kurtosis factor 4, and that tells you a little bit about how the skewness, negative skewness tells you that there are more valleys than peaks, while a positive skewness is the opposite. So this is typically a run-in surface could look like this, and a honed surface in an engine, for example, may look like this also, with many grooves like this, but a pretty flat top land here, while this one is not very good from a tribological point of view. So negative skewness, I would say, is normally a good surface for tribology. Kurtosis tells you also about the peakiness, how many peaks and how sharp they are. So a kurtosis higher than 3 is also not very good from a tribological point of view. There is also some attempts to study the wavelengths. If you have a profile like this, you can use some Fourier transform to find the amplitude at different wavelengths. That may also tell you. This is a way to filter, by the way. If you have the form inside here, you can filter it out. But you can also learn if you have many, as we will learn later, short wavelengths are not very good for a tribological contact. And if you have high amplitude and short wavelengths, that's not a good combination. So that could be that's also a way to describe it. I'm saying all the time here that it's a good way to do it. I can't really say what's the optimum way, because first of all there is no optimum way, but there is always a good way for a certain application. Yeah, this is just a few pictures showing some difference in appearance for different surfaces. And these are another set made here at the university. You can see here the appearance of ground, cross ground, shot peened, chemically deburred again. You can see that the appearance is pretty different. So it's and of course then it's also very difficult to find one or a few parameters that really describes that difference. This is from Hutchings' book, showing how the different engineering surfaces have different skewness and different kurtosis. So as I said, negative skewness is normally good for a tribological surface. So a honed surface, that's what you do in a cylinder liner in a combustion engine, for example. It has a negative skewness like this. While a turned surface without any after treatment, it has a positive skewness, and you should then use some grinding to get rid of that positive skewness. You can see here that if this is a turned surface, these are the ground surface, you actually move them to a negative skewness when you do the grinding. Yeah, coming back to RA values, just to show the difference in after different surface finishing techniques. You start with you can go down to the very fine surfaces. Well, when you use honing, polishing, and lapping, that gives you maybe the lowest RA values. If you have a RA value of 50 nanometers, which that's a very smooth surface, and it's probably shining like a mirror. Can still be, doesn't need to be, depends a little bit on the wavelengths. can be very smooth without be mirror like. The 3D, the 2D roughness parameters, they are called R, but you can find the same or the corresponding parameters also for the 3D. They are called S. So you can find the SQ, the SA, the SKU, which is the kurtosis, and S delta Q, which is the slope, but in 3D now. So you can find the same type of parameters also in the 3D world. Just a few pictures here showing some tests made here at the university. Here you have different surfaces with different surface roughness. So if, for example, the surface C has a much smoother surface than the other two, A and B, and this is a Tribological curve. So here you have a boundary lubrication. Here you pass through to mixed, and down here you have full film. And you can see that the change, it influences the transition to full film very much. The smoothest surface have a earlier transition to full film. This Sommerfeld number is proportional to sliding speed. So you can see that the transition to mixed lubrication starts almost 1 order of magnitude at a 1 order of magnitude lower speed than for the other two surfaces. And this slide shows a little bit the problems with measuring surface roughness. It's a comparison between an AFM and optical instrument, the WLI here in this slide. And you can see that these are the Abbott curves, the bearing ratio curves, and that you can see that you get a little bit slightly different and pretty big difference actually between surfaces by using different tools. As I said, this is a piston ring, by the way, and this is for a cylinder liner. This is for the unworn, and these are the worn. So you must be cautious when you use these tools. I can't really recall how big spot we measured here with the AFM in comparison to the optical instrument, but still you must think about what do you want to use this measurement for. This is a simulation result, and shows that again RA is not a perfect measure. It's about predicting the degree of mixed lubrication, and in this case it's a RA of 2.5. In that case we predict the degree of contact, the degree of boundary lubrication to 50%, while we take another surface with a lower RA, we can predict it to 70% contact, still a lower RA. That's because in this surface it's much peakier. You have sharp peaks like this instead of having sharp valleys like this, and this is not at all beneficial. While this surface has even lower RA, and it seems to have a surface roughness distribution which is more beneficial for getting full film. And finally, just a movie showing, I hoped at least to show that, but it didn't work, I'm afraid. Oh, sorry for that, but I will show it later sometime. So that was the end of part 2. I hope you have learned something about surface topography, and if you haven't, you just come back and ask me. Thanks a lot.